All right, and we are live. Hello, everyone out there on the internet. Welcome to the Swift Kick Show. I am Kevin Griffin, your host, and I am joined today by Ankur Kalra. I tried really hard to say your name correctly the
Perfect.
first time,
You got
so
it perfectly right.
awesome.
Yeah, yeah.
We'll give folks a moment or two to get in and get comfortable. I know we have a really thought-provoking, engaging presentation ready to go. Now, why people come in, I'll put up my slides. So let's see if this works. Cool. Well, it kind of worked. Awesome. So those of you who have never joined us before, this is the Swift Kick Show. This is a bi-weekly show that we do that showcases technologists and experts in the industry. I don't know why my slides changed, but there we go. It's basically all run by my company, SwiftKick. I got my start in the software developer community, going out into the world and teaching people everything I know and learning from people who were gracious enough to basically regurgitate everything that they know. And this show is basically a continuation of that goodwill that I've gotten from the community. I just want to give back. So hopefully you get something really useful out of this presentation. And I really hope that you join us for future presentations. We're on the social medias, specifically Twitter, LinkedIn, Facebook, but we're really trying to push our YouTube channel right now because we are desperately close, like 4, maybe even 3 people away from that magic 100 subscribers that you really go for when you just start a channel. If you haven't subscribed, I would plead with you to please go subscribe, because once we hit that 100 subscriber mark, we can get a vanity URL and we won't be just youtube.com/c/xy521, whatever the hash is for
Is that
our
actually your
channel.
hash? That would be awesome to
No,
know.
no. If I could regurgitate that just off the top of my head, I'd be amazing.
Yeah.
But go to YouTube and just search SwiftKick, look for the boot, and subscribe to that channel. As I said, we do this every couple of weeks. We have 2 upcoming sessions that we know about. Last week or 2 weeks ago, we didn't know what we were going to talk about. But a good friend of mine, John Athaday, is going to be speaking with us about 5 fast fixes for your app's user experience. John is a UX professional, and he does amazing work with his company, Metaculous. And this is guaranteed to be a good time, especially if you're a developer and you don't claim to be a designer or have any sense of what good UI or good UX would be like. John's session hopefully will give you some tips. A couple of weeks after that, we'll have Mr. Matt Groves. Matt works for Couchbase, and he'll be talking to us about NoSQL. And if you've done any NoSQL in your past, NoSQL usually means no security. You can just go in and do whatever you want to. Matt's going to talk to you about why that's not really the case and how you can properly secure your NoSQL databases. But we're happy today to have Ankur with us. He's going to be talking about unbelievable and complex advancements in machine learning. And Ankur, before we get started, I just want to ask you a couple questions and give our viewers a chance to learn a little bit more about you. Those of you we have some folks in the chat. So again, if you have any questions, post them in the chat, and I'll interrupt Ankur as he's talking and make sure he gets you an answer. If not, we'll have a little bit of Q&A at the end, as long as we have time. But Ankur, just to get started, tell our viewers a little bit about yourself and where do you work and what do you do?
Yeah, awesome. And thank you for having me. I'm really glad to be able to talk to you guys about the stuff today. So again, like as Kevin mentioned, my name's Ankur. I run a machine learning consultancy and a product studio here out of Atlanta, Georgia, which is bright and sunny most days of the year. If you're not nearby, I highly recommend you come visit. I started actually doing software work. I grew up in Dubai and all over the Middle East and India. My family was traveling a lot. But what I really loved about computers back then was that, for a little kid in Dubai, which is really hot most of the year, it's an opportunity to construct new realities. And so I started programming and building things that not only I'd never seen before, never existed, but no one in my school and my family had seen before. And that was really fun. It was cool. It was like building. In particular, my dad's an architect and he builds actual buildings, real buildings. And so for me, it was awesome to build these like virtual things that my dad knew nothing about, right? That really pissed him off. And that was really a rewarding thing to be able to be like, look, Dad, new tricks. So that was really fun. And then I spent a lot of time at Georgia Tech and University of Illinois, and was very fortunate there to be able to work with some really great people and learn from them. That was very rewarding. And then most of my career has been guided by this arc of, technology is doing this really interesting, fabulous stuff, really, really powerful things. And yet, my grandma still can't check her email, and, sort of like very basic problems haven't been solved for large swaths of humanity. So there's some of us that get to live in the future, and it's really cool and it's really exciting. That I'm really motivated by how can we take all of this technology and make it transformative for people whose lives could be transformed. And so just as an example, I like to talk about, like, I carry a computer with me all the time. It's an iPhone. It's really powerful. I have all the skills necessary to bend it to my will, but I can't get it to tell me what time it's going to be before I can call my aunt in India or my parents in Dubai. It's smart enough to do that, but there's no way to do that. And so trying to find ways to get technology to be more in service of their users is sort of the larger goal. Machine learning is a very powerful way towards that, and that's what I've been exploring recently.
I love it's an old Reddit joke, but it's still worthwhile. Is someone asks if you could go back in time 100 years and tell the people 100 years ago about something today, what would you say? And someone responded that says, I possess a device in my pocket capable of accessing all known human knowledge, and I use it to look at pictures of cats.
Yes.
And it really hits home, because it was probably looking at a picture of cats
Right.
before I read that. So I know exactly what you mean.
And for that purpose, I introduced an obligatory cat pic in my presentation, just to be, native to the internet. But it's there.
Fantastic. So Ankur, outside of software technology, do you have any hobbies? Anything that's not technology related?
Yeah, and I try very hard to keep them not technology related. I got really into biking last year, and it's been awesome. I'm in the best shape I've been in years, which isn't saying much. I'm a technologist. First I got really into biking, and I was like, oh, I could get a computer, and I could like map my rides and start doing all this computation. And then my fiance was like, the whole point of biking was to get away from the computer, so let's not make that hobby a technical one. It's been really fun. I think it's really important to make sure you have things that you're not good at. You're always like, I strive to always have something I'm a beginner at. It keeps you humble, teaches you something new. I think it's important.
Awesome. So in your business, what kind of tech stack do you all use? Do you have one particular stack you always go to, or do you have a variety of things?
That's a great question, and it changes. So our business has two practice areas. The older practice area is the product studio, which is where we build sort of like MVPs and mobile apps and web apps for folks. Typically sort of React Native or Rails, depending on the needs. We do a lot of serverless work. That's been really fun. And then we do also some like distributed scaling work. And so, the kind of stuff I did at Amazon, I used to work at Amazon for a long time and built large scale systems. And so we do that for some of our clients, and that's usually like cloud machines on AWS. And for our startup clients, we use Heroku. But the newer practice area, which is what I'm talking to you guys about today, the machine learning work we've been doing for the last couple of years now, that's all CUDA, which is fascinating to me. There's, I don't know how familiar people are with machine learning, but if you Google like machine learning 101, there's a lot of conversation around, should I use TensorFlow? Should I use Keras? Should I use Python? Should I use Torch? And they're all just like syntactical sugar. Like underneath the hood, they all use the same machinery. They all use CUDA, which is this NVIDIA driver stack. And so that's what we build on for both in-house laboratory experiments and production deployments.
Awesome. So last but not least, you're talking about machine learning, and that's kind of a big, kind of the next big thing, I think, in computing. But is there any other technology that you kind of see as the next big thing? If someone's looking to really pad out their resume and
Sure.
make 6-7 figure salaries, what should they do next?
Yeah, that's a great question. I have an unpopular opinion here, so I'm just going to share it. Uh, I don't fully know that I would bet on Bitcoin as both as an individual or as a technologist, right? I
Hmm.
think the blockchain is incredibly powerful and interesting, but there are still it's still a solution looking for a problem, and I think we're going to go through several rounds of iteration on that before it's something that's a useful skill for someone immediately looking for a job. On the other hand, I think virtual reality is just coming around the cusp. Like augmented reality is doing really well on iOS devices these days, and you can build some really powerful experiences because, in part, machine learning has become so easy to do. But I think that's really compelling. So we do mostly machine learning, but a lot of the math is similar and a lot of the hardware is similar. And we've just started asking the question, like, what embedded experiences can we unlock now with this technology? And a lot of them are in the VR, AR space. I think in the next couple of years, we're going to see a lot of leaps and bounds there too.
So go see Ready Player One when it comes out in theaters,
Right.
because that's not really a movie; it's a documentary about the future, the way things are going to be.
I love that. That's awesome.
Well, awesome. Thank you, Ankur. Well, I'm going to go ahead and let you get started. Again, anyone out there, if you have any questions or you want to kind of lead the conversation, just post something in the chat, and where appropriate, I'll interrupt Ankur and get his take. But with that, go ahead, sir, and let's see if your presentation works.
Let's find out. Can you guys see that?
I see it.
Perfect. Awesome.
All right, I'm
So
going to turn off.
Okay,
All right.
cool. So what I'm going to talk about today are some really unbelievable advancements in machine learning that have come out in the last year. I'm going to, in particular, dive deep on one, but you don't really need to have a deep mathematical or machine learning background. I'm going to give you guys a little bit of a flavor of the background just so we're understand each other when I'm using some terms. But this is not going to be a rigorous mathematical conversation at all. The whole reason to have this conversation is because some of the things we're doing in machine learning, as awesome as they are, raise some ethically complex questions. And I think like the work I'm going to be presenting today is both technically complex and ethically complicated. And I think it's important that us as technologists should both be familiar and understanding the trade-offs that are being made here, but also can act as ambassadors, like informed ambassadors, to explain to our societies and our friends and communities what the implications of some of this technology are. Because if we don't, I think we may end up in a world where that's not exactly the one we wanted. And so just before we get started, I'd love to get a sense of who's in the room, how deep an experience people have on the technology. So have any of you done any sort of machine learning work at all? Because if so, I want to make sure I don't waste a lot of your time talking about the basics. Let me see if I can get into the chat here. So anyone done anything with a sort of linear algebra background or high school calculus? A refresher of that? Okay, great. So we got some folks that have done some like Azure ML, perfect, some R, that's great. Those are all like very promising. Great, let's get started and we'll just cover off on the basics. For the folks that have no mathematical background, I'll give you just enough to keep abreast of what we're talking about here. And if you don't understand all the details, that's totally fine. I just want to make sure you have some of the context of the words are familiar when we talk about slightly more complicated things. So just to start with some basic terminology. And for some of you that do know machine learning, you'll notice that I've simplified things to the point of maybe being slightly technically inaccurate, just for the purposes of making this accessible to a wider audience. So let's start off with sort of this standard looking thing. It's an XY graph, just a standard 2D graph. And the key thing here are, there's two different dimensions, X and Y. And then this is an example of XY graphs you may have seen in the real world. These are literally the first 3 Google image search results for XY graphs. But it's a great way of plotting how one variable changes as another one does. So in that terminology, X would be an independent variable, like the day changes unrelated to what we do. but then the temperature changes based on what day it is. And so y would be the dependent variable. So that's an XY graph. This is also an XY graph, just with a recentered origin, just to drive home the point that X can also be negative, which is, if you don't have a mathematical background, that might be the first time you're hearing that. X and Y can both go negative. These are points on the graph, right? And so each point has an XY coordinate. That tells you where in the graph to draw it, and it represents an individual record or data point in your system. And this is a line. Unlike the colloquial definition of a line, in mathematics, a line extends infinitively. That's the wrong word. Infinitely in both directions. That is to say, the line doesn't stop either in the X or Y direction and goes on forever. The line that stops, that's called a line segment. We're not talking about that. That's geometry. For our purposes, a line extends infinitely in both directions. The key thing about a line is that there are an infinite number of points on the line, and they all share a relationship. In particular, the y value, the y coordinate of each point shares the exact same relationship with its x coordinate as every other point on the line. That is, in fact, the definition of the line. Mathematically, we express that as y is equal to mx plus c. Don't worry, we're not going to get too deep into the math. All I want you to understand from this is x and y are placeholders. You fill in a value of x, you get a value of y for a given line. M and C are parameters. They define what line we're talking about. And so two lines that have the same values of M and C are the same line. And if they don't, they're different lines. But a line definition will always be y is equal to some constant times x plus some other constant. And so for any given line, if you give me an x coordinate with one multiplication and one addition, I can tell you the y coordinate. Again, super simple example. These are made-up graphs in Keynote, so they are not to scale. But this is the line y is equal to x. So I multiply x by 1 and I add 0, and I get a line at a 45-degree angle through the origin. This is y is equal to 2x. And so I'm doubling the x at each time, and you get a slightly steeper line again through the origin. This is y is equal to negative x. And so it goes in the opposite direction. And as you can tell by the last few slides, as you change the multiplier, you're spinning the line around the origin. And you can, if you're not already convinced, you can convince yourself that as you change the multiplier, you express every single line that could be expressed that goes through the origin. And then if you add a constant, you can also express lines that don't go through the origin. And so y is equal to x plus 1 would express this line where, if x is 2, y is 3, if x is 3, y is 4, and so on and so forth. But these two parameters, the multiplicative constant by m and c, which is the y-intercept constant, are sufficient to describe any 2D line that we may care about. Any questions so far? This is some basic stuff, but I don't know if we have people without a math background, so I'm going to start covered off on that. I'm going to keep going, but let me know if there's any questions along those lines. So just to drive this example home, we're going to draw a 2D graph and imagine you're in the housing market. You're buying a house and you plot the purchase price of 5 recent houses against their square footage. And so houses are as big as they are. That's an independent variable, but the price of it is dependent on how big they are, at least to some level. And again, this is not a graph that's to scale. I just made up numbers. But these 5 data points would represent 5 distinct houses. The cheapest of which went for $420,000. It was 2,000 square feet, and the most expensive one of which went for $2 million. That was 4,000 square feet. And so you could draw a line that comes as close as possible to these points. And in particular, you can measure how close it gets to each of those points. And now this line, which is representing the information you have learned from 5 distinct data points, can be represented again by just those 2 variables, right? M and C, which tell you the slope and the intercept of the line, the multiplicative factor and the additional factor. And then for any individual point on the line, can you guys see my cursor? I don't know if that shows up for you. I'm going to assume that it doesn't. For any particular point on the line, if you give me the x coordinate of, say, this 3rd point, using the equation of the line, I can tell you the y coordinate, and I'll be wrong because there is some gap. And in general, the goal is to be wrong as little as you can, so to minimize the error. And you try and find a line that is as close as possible to all of the data points that you have. But the key thing here is that you've gone from 5 or 50 or 100 or 200 data points, which express some reality about the world, into a model, which is not those data points, but is informed by those data points. But it's a mathematical equation that you can then use to make predictions in the future. And as part of the modeling process, you are going to make some mistakes, right? Like this is the error that we're seeing. But once you have the model, you can ask interesting questions, such as, given a specific square footage, and so I don't know if you see there's a new point at the very end of the line, given a square footage, what should the price be? Like, what is a good average price to expect? The model lets you ask that kind of question. This is sort of this kind of a question where you're predicting a quantity is what we call a regression in machine learning. The thought being that given some historical data you've learned to model, and given a model, you can now ask it to predict some specific number. But you can also ask the other question, which is, given a square footage and a price, is this a good deal? And so the key thing about the line is that not only does it tell you what the y-coordinate and the x-coordinate on that line would be, it also divides the space, in this case, into two different categories. And so everything above the line is, in some ways, more expensive than average for that square footage. And in some ways, everything below the line is less expensive than average for that square footage. Assuming, of course, that this model is correct and represents the true underlying distribution, which it may or may not. Any questions so far? Does that make sense? The key idea here is that you've taken a bunch of aligned data. And by aligned, I mean data for which you know both the inputs and the outputs, the square footage and the price in this example. Use that to learn some underlying mathematical construct that approximates that data, and then use that mathematical construct to either predict or categorize future data that you haven't yet seen. And this, is the very most simple thing. It's linear regression. It's not really any machine learning construct, but we use a lot of the same terminology in the same way, and some of your intuition about error and data and modeling will transfer between this and what we talk about. So I want to make sure we're using the same terms. Linear regression itself, you can do that in Excel. People have been doing that in business schools for decades now, or at least however old Excel is. But anyway, linear regression is very simple. It shares, it's, even for how simple it is, it has a lot of power. It's used very widely, even in sophisticated industries like insurance. But it also comes with a bunch of what I'm calling simple problems. And so I'm not going to go into the detail of this. We can look into it. I'll share the slides later, and you can read through them if you want. But the basic idea is that the model is trained on the data you present to it. And so your data may be biased. And for instance, there may be some intrinsic bias in transactions. If people are irrational for houses that are over 10,000 square feet for some reason and pay more than they really should, that irrationality would be expressed in the model, and the model would predict irrational prices for houses over 10,000. So it's not claiming that the model is good in a sort of rational or independent definition. We're just saying that this model is going to try and approximate a price based off of historical data, not necessarily based off of true value. So the data itself could be biased. You could be measuring the wrong things. Maybe it's not square footage people care about. Maybe it's number of bedrooms. You may be missing key things like location, or you may have modeled things poorly. So you may have used location as GPS coordinates, but people really just care about like distance to a school or something like that. And then, again, we chose a linear model with one variable. Obviously, that's not sufficiently powerful. You may care about, you may need a more powerful model using more variables, still a linear model, but with more variables, or alternatively, a nonlinear model with different variables. And then you can actually go the other way as well, where you have too powerful a model. So, if you pick an extremely nonlinear model in a high dimensional space, but you only have 10 data points, you're not going to learn anything useful. And so you kind of have to match the the data to the strength of the machinery you're using for it. And there's very many other errors of that type. But the thing that's shared across all of these errors is that we understand them. As machine learning practitioners, we're trying to drive them out. They're all captured in some way in how we measure the accuracy or error of our systems compared to ground truth. Then we try and understand the transferability of our models. We're thinking about all of these things. These pose very real ethical questions, right? Like, do you want to preserve the bias of conviction decisions or whatever else, or how do you solve for that? Especially in self-guided cars, self-driving cars, and self-guided missiles, there's a whole lot of questions that are hard to answer in a good way. But these are all questions that we as a community are already grappling with. What I'm more concerned about are an entirely new class of errors that are slightly more insidious, and that have sort of only recently really begun to attract attention. And I want to make sure that you guys are understanding and are aware of the complexity there. And so before we can get too much deeper into the specific paper I want to present, we need some basic machine learning building blocks. And so right now we looked at a linear regression model, which is a way of saying, or even just like a line is a way of saying, for a given X value as input, I can give you a Y value as output. That's the equation of a line. You can certainly extend that to multiple inputs. And so if you give in multiple things, compute some transformation that combines those things. And what that computation is, we don't have to get into right now. This is glossing over a fair bit of detail, but this is roughly what a perceptron does. And then if you align them in a specific way, you get this idea of a neural network. This neural network is very simple. It only has 2 hidden layers. Sort of production neural networks that we deploy typically have several hundred hidden layers. This neural network only has 4 nodes in each layer. Ours have thousands of millions. But this is basically the idea of how neural networks are shaped. Please do stop me if you want to dive deeper in any of this, or find me afterwards, and I'm happy to talk your ear off about how any of these are constructed or trained or any of those things. But for today, I want to talk about a very simple thing that I want to make sure that you understand about how neural networks actually work, which is you take some data that you already know the answer to, right? Like housing prices that have recently been sold and square footage. You feed the input, and in this example, there's 3 unrelated pieces of input that you feed it. And then you transform it through the network with, initially just completely random parameters. And then you compute an output. And this is like what you think the price should be for that square footage. And it'll be completely wrong because you don't know anything about the world the first time you do this. But you know the answer. And so you, as a trainer, compute the distance between the output and the actual price that house actually sold for, use that as an error, and then you do back propagation, which is saying you take that error and you distribute it through the different layers and say, how should have these nodes or neurons or perceptrons done their transformation so that for this input, I got the right answer. And so every time you process one input through this network individually, if you were doing them one at a time, which we don't actually do, but if you're doing them one at a time, every time you see an input, you see what output the network as it currently stands, what it's giving you, you see how off that is, and then you try and correct how the network currently stands so that it would have given you the right answer. I'm not a military man, but someone told me this is similar to how snipers trace their bullets. Like they fire one off and then see where it lands and then try and correct from that. So it's a similar sort of thing there. The key insight that happened in 2012 was that, well, let me back up. This is my obligatory cat pic. This is the only one in the entire image, in the entire presentation, so enjoy while you can. But as most of you know, if not all of you, images are basically just arrays of numbers as far as the computer is concerned. There's 3 channels, red, green, and blue, and intensities for each channel for each pixel coordinate. But you can think of it as a giant array or 3 arrays of numbers. And so in 2012, AlexNet was introduced by a guy called Alex, whose last name I can't pronounce. And he came to the insight that neural networks are operating on numbers. Images are basically just numbers. We can use this idea of convolutional neural nets to operate neural nets on images. And so in this example here, the red block on the very left is an image with 3 channels, red, green, and blue. And the blue block is a volume describing a population of neurons that are operating on that image and doing some transformation to individual pixels on that image. And we can get into details of that in a minute if that's useful. At some point, it switches from the visual to the fully connected layers, where now it has determined some high-level mathematical representations of features on which we can actually do a classification or regression and build a model. It's not critical that you guys understand all the details, as long as you understand in concept that on the one hand, you can feed an image, apply a bunch of transformations that are fairly complex and need to be constructed in a certain way, but are very flexible, and then ask it to give you an answer at the end. And obviously, the very first time you ask for an answer, it's going to be completely wrong. But if you actually know the answer, you can figure out how wrong it is and use that error information to try and get these things correct. And so if that sounds like it's really hard for the network itself, this structure of neurons and parameters and transformations, to learn anything useful, that's true. It really is. And so when you start with one image, you don't learn anything from that. But about the time you've gotten through like 10,000 images and augmentations of those 10,000 images, your network's starting to learn some useful things. Production neural networks that we've deployed are often in the hundreds of thousands of images, it's been trained in hundreds of thousands of images, and are on each image very many times before it's starting to learn something. But the key insight here that sort of came out in 2012 was that this idea of a neural network can be applied very successfully to images. People sort of always knew that, but couldn't actually feasibly implement that because the computation for an entire image and these kinds of convolutions is quite complex and intractable in ways. But in 2012, AlexNet showed that we could implement all of this on a GPU. And GPUs are becoming affordable because of video gamers. So really, machine learning resurgence is really because of video gamers. And so I think we all owe a debt of gratitude to everyone that plays video games. This is a sort of clearer image of the convolution neural network. So like it's operating on an image on the left. There's a bunch of stages, the feature learning section, where it's actually transforming that visual pixels into multispatial and multidimensional versions of those visual features. And the way to think about it, this is sort of the example I use when I describe it with my family, is think of it like you peering at an image and looking at it and a bunch of like pulling it up close to your face, moving it further out, squinting at it, rotating it. The sort of the convolution layers are doing the equivalent of that in many ways, and doing all of them in parallel simultaneously in a variety of different ways. And the classification layers have like taken all of that data, distilled it down in some relevant mathematical feature space that we then use in relatively few, very shallow, fully connected layers to actually do classification. In this example, in this network, it looks like this network is trying to classify vehicles. And so as you see on the very right, there is this sort of one-hot vector representation where the way to think about it is there's an array of, I don't know, like 20 elements here. And, you know, if it's a car, the first element will be 1 and all the other will be 0. If it's a truck, the second one will be 1 and all the other will be 0, and so on and so forth. And so in this particular network, the classification that is domain dependent, which is about cars and trucks and vans and bicycles, is only the very last few layers. All of the stuff up front is really just teaching the network how to see. And so understand the fact that there are such a thing as colors and edges and circles and patterns and curves and things along those lines, which is really fascinating. That's a key insight that the community has come to, is that you can take a network that was trained to see, you know, cars and vehicles and trains of various sizes, and the bulk of the machinery and the bulk of the complexity is in teaching it how to see. And so if you want to teach it how to see faces or how to see plants or something else, you can just throw the last few layers and continue training in a completely different domain. And all that logic about how patterns and shapes and colors and lines and curves and edges work transfers right along, which is huge and very rewarding. It's not a thing we had in the earlier stages of the industry. So when you understand this, the key thing, I want to go back to the previous slide for a second here. The key thing is, like, you and I look at the image on the left as an image. It's a JPEG, but to the computer, it's just numbers. And we have on the very right this idea that the first element of the array represents a car if it's a 1, and if everything else is a 0, and the second one is a truck. But again, to the computer, it's just numbers. It's feeding mathematical transformations all the way through and then backwards to propagate the error all the way back. And so once you're doing numbers all the way through, you're not restricted to just coming up with a numerical or a class-based answer at the end. There's this very cool concept called autoencoders that I wish I could talk about in more detail. But you can also use the same technology to give you back an image, maybe even the same image that you started with. And so you feed it an image, again, red, green, blue. You force it through this network, and then you reconstruct an image, maybe the exact same image, which may seem like it's not very useful, but there's a lot of really cool things you can do with it. So if this image, for instance, is of an eye, and you started with an image of an eye, and you've trained the network on this kind of a thing, the key thing to notice here is this dark gray box in the middle. I don't know how to point to it using Webinar Jam. But the dark gray box in the middle is smaller and deeper. And what that does is it's forcing the network to learn something salient about the image. It's forcing the network to describe the image in a more concise way than the image itself. And so what that means is it's asking the network to learn what's important and what's irrelevant, and to forget the irrelevant details, but preserve enough of the important details that it can reconstruct the image on the other end, fairly close. And as you see, you'll see this image is a little bit blurry relative to the input, and it's a side effect of a deconvolution network, which we can get into a little bit later. But overall, the images are fairly close representation. If I were looking at the left image and asked to pass a note to you that described it in sufficient detail that you could draw it, I don't think I could describe that eye well enough that you would draw it in as close to detail as this network has done. And this is a relatively simple task for an autoencoder. Here's an example of how you can actually productionalize this technology. So in this particular image, the researcher has introduced a fake crosshair over the image. But you see this problem all the time with historical records or with OCR technology. The page you scan or the page you're looking at may have blemishes or artifacts from how it was imaged. Either like the camera had speck of dust on it, or the page was torn, or whatever. And this reconstruction, because it's been trained on remembering the important parts and forgetting the trivial details, like the blemish, it can reconstruct what that eye looks like in the same way that you or I reading a wrinkled piece of text can ignore the wrinkles and focus on the important bits, which is really cool. The fact that networks can do this in an almost automatic way is kind of amazing, kind of powerful. We're not going to get into too much detail here, but I just want to give you examples of other things we've done. By making the network learn important things about how color works, you can give it a black and white photo and ask it to colorize it. And we've seen some stunning results there. And the bottom row is something that I would have told you is black magic, just like a decade ago in my own career. You're taking a low resolution image on the left and converting it into a higher resolution image. You're getting almost something for nothing in some ways. You can always scale up images, right? Like you can do that in PowerPoint or whatever, and it always gets blurry because there's, you had 100 pixels and you're trying to fill 1,000. There's no more information to get a sharp image, except that there is. Like a trained artist could do that, as can this network, because it's learned what images and colors and textures and skins and boundaries look like. And so it can make intelligent decisions about how to still preserve a sharp image. There's a multimodal problem that we're not going to get into, but if you're interested in this kind of stuff, please do email me and I'll send you some links. Anyway, so that's an autoencoder. The more commonly used version in practice is called a variational autoencoder. But as long as you understand this high-level concept, I think that's enough for right now. I want to make sure one last thing about this that you do understand is the thing we get on the left is, a picture, a JPEG, or an image that our computers treat as an image that we can visually understand. And the thing we get on the very right is also a picture. The thing in the middle, though, is a succinct representation, a mathematical representation of that same picture, but it's not human interpretable, right? Like it's a collection of vectors in a high-dimensional space that if you gave me, I couldn't tell you what to do with, except that pass through the network to see what it actually looks like on the other end. So that's how autoencoders work, and the to us, it's image in, math in the middle, image out. To a computer, it's just numbers in, numbers all the way through, and numbers out. But the fact that we can interpret it as image in, math in the middle, and image out means we can also do the opposite. And so we had this idea of a generative adversarial network. And actually, before I get to this slide, let me show you this next version. It's not critical to understand the details, ignore the mathematical notation. But the key idea here is you start with some mathematical distribution on the very left that you may or may not understand. And you can use that to generate an image first, and then have another network that looks at that image and generates some math. So from a shape perspective, it's sort of the inverse of the thing we were looking at, although it's used very differently. In this particular example, you're using a mathematical description as described in the blue, that represents a flower with a small round violet petal and a dark purple center. And the network is able to generate an image that does that. And then you have a discriminating network that's looking at that image and can translate that into a representation that says the same thing. I actually stole this image from a paper that has a much more powerful and much cooler thing, but the image was clear. That's why I stole it. But the way to really think about generative adversarial networks, also called GANs, is that they operate in this two network sort of model where the two networks are in some ways competing and in some ways cooperating. So the first network is this G, this generator that's making fake things from effectively random noise. And so, you're feeding it some mathematical representation and some noise, and it looks at that and says, here's what I think, a flower looks like. And then you have a discriminator that's saying, is an image that I'm looking at a real image of a flower, or is it something that the generator made up? And obviously, the first time you run the generator network, it's going to give you basically something that looks like garbage, and the discriminator will have a very easy time. But here's the key. The discriminator makes a decision, and based off of whether the discriminator is correct or not, and you know this because you're the trainer and you're choosing where to feed it an image from, you can compute an error, and you can feed that back not just through the discriminator network, but through the generator network as well. So through both networks, it's like a teacher that said you were wrong when you drew an image of a flower, but also told you how to make it better so that it looked better next time. So if you're cynical, sort of the metaphor that people use to talk about this is like, generator is like a counterfeiter trying to make fake bills, and the discriminator is like the policeman trying to detect, is this thing fake or not? And it's a cat and mouse game. As the discriminator gets more and more powerful, the generator gets more powerful, and vice versa. And because they're sort of linked in this way, they're able to sort of share insights. If you're an optimist, the interpretation is the first one, which is, the generator is a student, the discriminator is a teacher. That gives you great feedback, enough feedback that you can actually tune your network to get better at producing things that look like the real thing, which is kind of amazing. Little sidebar, the generative adversarial network architecture is fairly recent. I want to say like 2014 or 15. But it's the result, I could be wrong on the day, don't quote me on that. It's the result of like a bar bet. I think like someone was in a bar, had this idea, ran it past someone, they didn't think it could work. And I think he says he went home that day and coded it up and like went to bed and looked at it the next morning and said, oh, it actually worked. Kind of amazing. It's really cool. There's a lot of really cool things you can do with GANs, but I just want to make sure you understand the high-level idea of you have these two competing networks. It's sort of a zero-sum game. As one gets stronger, that's because it's exploiting some weakness in the other one, and so the other one gets stronger, and the first one has to get stronger again. And the other key thing is that the error is differentiated across both networks together, which means that when one network learns that it was wrong, it shares its notes. That's really where the key thing comes from. There's some more details on how the gradient update works, and in practice you end up throwing away one. Those are irrelevant for right now, but I want to make sure you understand that. And I think with that, we have all the building blocks we need to talk about sort of this paper that I really wanted to talk through with you guys. Before I get into that, any questions so far? Anything that isn't super clear? It's not critical that you understand the math or any of the details, although I'm happy to talk you through that later if you'd like. But I want to talk about this paper real quick. Okay, so this paper is called Unsupervised Image-to-Image Translation Networks. It came out of NVIDIA in December 2017, so it's very recent, only a few months old, and it's fascinating. It's motivated by this research question that people started with, the researchers have been chasing down for a couple of years. Is clearly these networks are learning something. They're becoming intelligent in a way that we can all agree is useful. But could they be more intelligent than just like predicting the price of a house or classifying whether something is a good deal or not? Could they do something novel? Could they express some form of imagination in particular? And imagination is a tricky word, but let's just say someone comes up to you and says, hey, I have a cool startup. It's called something, something, something. It's like Uber for lawnmowers. In your head, you're doing some imagination. You don't really know what the startup looks like, but you know what Uber is and you know what lawnmowers are. And you don't have all the details in your head. The details are fuzzy, but you understand at a high level what that thing looks like. So the researchers here are trying to chase down that question. Could we build something with that level of imagination? And they did. They really did a really great job. And so here's an image of a car driving down a sunny street. It's a dash cam photo. This is a real image from the real world. They asked the network to imagine what would it look like if you were driving down the exact same car with the exact same configuration of cars on the road ahead of you, but it was night. I got this image, which is kind of stunning. Like you'll notice the street lights are turned on, the headlights are turned on, the tail lights are turned on. Even the reflections in the hood look like, or on the hood, look like a nighttime scene. But that's a completely synthetic image that the network imagined from nothing else than the image on the upper left. That's amazing. That blows my mind. This network never saw this scene at night, and it never saw, the same scene, any scene, but the same version of that scene in both day and night. It just saw a bunch of day images on YouTube and a bunch of night images on YouTube that were completely unrelated to one another, but understood how streets work at night and how to translate one street scene and into a night version of that image. Blows my mind. This is amazing. Same thing, another straight summer day, bright sunny day. Now it's asked to imagine it's a rainy day. And you'll notice like the cars are on a wet road now. The road has some reflection. Even the light pole is a little bit darker. The sky is overcast. It's amazing how well the results actually work. Another example, another sunny day in, I have no idea, maybe August. And it's asked what is the snowy version of that day looks like. It's introduced this weird tint that's interesting, but it also shows snow. It shows snow both on the side of the road, but also on the road itself, on the sign. The trees are bare. It's figured out that in the wintertime, on a snowy day, trees tend to not have leaves on them. And it can go both directions, which is kind of amazing. It can add leaves to trees that didn't have them. Again, this network knows nothing about trees, knows nothing about snow. It's just seen a bunch of images in two different domains and knows how to translate between them without any supervision. That's amazing. The question is, how does all of this work? And now the key machinery in this paper is this diagram that I have up. It looks scary, but now that we have all these building blocks, it's actually very simple to understand how this thing works. And we're going to go super quickly on this just to make sure you understand the high level. We're not going to get into any of the math. So the first part of this graph is this upper piece here. That's not scary. That's just an autoencoder that we already saw. So you give it a bunch of images of sunny days, and it reconstructs the exact same images of sunny days. That's not hard. We sort of already understand how to do that. Same thing at the bottom. You have another network, E2, G2. You do the same thing with night days, right? And so you give it a bunch of images of nighttime scenery, and you draw a bunch of images of nighttime scenery. Again, not hard, just another autoencoder. And that covers more than half of the machinery. The key insight, though, is that both of these autoencoders share an internal representation. In some ways, they're sort of trained and forced to use the same vocabulary. And the paper does some really interesting tricks to make that work, and we can talk about that later if necessary. But that's really all there is. So they're just two autoencoders that are tied together in this interesting way. That leaves this part of the network, but that's just, again, like we just looked at. It's a generator that's making images and another network that's trying to decide, is this a real image or one that came from the generator? And so you feed it some real images of sunny streets and some fake images of sunny streets, and it just says, which is it? Is this real or fake? And sometimes it's right, sometimes it's wrong, and you differentiate the error through the network. You do the same thing with the other side, again, now with nighttime images. It's another, again, same exact concept, and you're feeding in images real and fake, and the discriminator D2 in this example is trying to decide, whether the image is coming from the generator network or from the real world. And over time, as you train it, it gets better and better, as is the generator. And if you tie them all together, you get this really interesting machinery. So now you have these 6 individual networks, E1, G1, D1, E2, G2, D2, where G1 is acting as both the decoder for the autoencoder part of E1, G1, as well as the generator for G1, D1. And the same thing on the bottom for the alternate scenes. The top row is, you can think of it as doing, like, say, sunny images, and the bottom row is doing nighttime images, but they're all doing the same row. It's the same kind of thing. Once you have this, you can drop out parts of the network and say, hey, take this image of a sunny scene, encode it into this shared vocabulary, but use the decoder from the other network. And now that network knows how to draw the important parts of that image as a nighttime scene. And now you end up with this transformation that you didn't ever see before, you didn't specifically train for. You just use these very simple basic building blocks, and you've now successfully taught the computer to imagine what a nighttime version of the scene could look like, which is impressive and amazing and blew my mind. You can go the other direction. You give it a nighttime image and give it and get a sunny image on the other side. In particular, in the paper, they do the entire loop, circle to circle. So start from sunny image, get a nighttime image, feed that in on the other end, get a sunny image, and see if you got the same thing. And then try and minimize the error that way too, which is kind of cool and really compelling. So that's all built off of this network, which is based off of the building blocks we talked about. And it's all motivated by a very interesting research question, just like, can you make computers imagine? And the results are amazing. This is an example of saying, here's the dash cam video on the left. What would it look like if it were a video game? And that's a very realistic representation. You can go the other direction as well. Here's a video game image. Make a photorealistic version of that. And some of the details are a little blurry, but it does a pretty good job, at least enough to pass at first glance. If you go to the paper website, there's actually like videos of all of these operations happening in real time, which is kind of amazing. Here's how you can translate a particular dog, your dog, what it would look like as different dog breeds, which is really cool. They did this for a bunch of different species. They did this for cats as well. Here's what that cat would look like as a leopard. There's some really, really interesting results in the paper. And then here's another interesting thing. So the top row are all real images of real models, right? And the bottom, the middle row is those models as the network would imagine them with blonde hair, which is amazing. Like, it actually looks relatively realistic. It looks really good. I'm not saying it's 100% perfect, but the coloration is fairly believable. Like, it looks as real as something you would see in a magazine, which is already slightly unreal anyway. The bottom row is where it gets even more tricky. That's what those models would look like if they were smiling a little bit more. And so none of those models actually smiled in that way or consented to have their photo taken in that way. But the network can imagine them smiling that way and share that image in a photorealistic way. And that's where this technology that's motivated by a very pure question, using some really cool talks, really cool building blocks, ends up being a little problematic. The researchers certainly did not start out with that goal in mind, but that's how this technology can be used. You've taken someone that did one thing and made them appear to do something different in a way that, at least to the human eye, looks believable. What are the ramifications of all of that? We're not entirely sure yet. So there's some fun versions of this. Reddit immediately started putting Nicolas Cage in everything. This is Nicolas Cage as Indiana Jones and as Gollum. Again, this is something that now people are doing on their own, not researchers. The technology for it is now accessible enough that anyone can do this. For some reason, the internet got obsessed with shaving this guy's mustache. There's a long backstory to it, but it doesn't really matter. But again, very doable. Some guy did this with $500. Not even specialized hardware. Just did it on his machine under his desk. Didn't take a lot of effort. And then, of course, because this is the internet, there's a wave of fairly convincing but very fake porn generated using this technology, or at least using techniques inspired by this technology. And that's scary, and that's very problematic. If you look at this core piece of machinery and the core research question, like, can we make computers imagine things? You're forced to deal with the question that if we can make computers imagine things, then someone can make computers imagine things they really shouldn't, and make it public in a way that your imagination or my imagination may not be public. And that raises other interesting problems. It's almost hard to say things like we should have regulation against this stuff. You don't really know how you would, because the research came from a very pure question and certainly had pure intentions. But then it got deployed in this very negative way, and there's a huge media backlash against this particular paper that's undeserved in some ways, but very relevant in others. And that's a thing that I think is important that we all stay aware of. Machine learning is very powerful, and there are certainly ethical questions with just like what data sets we use and all of those kinds of things that are already being explored. But there's even more ethical questions, I think, around as we make it increasingly more powerful, what capabilities are we unleashing in the world? And I don't have a good answer. So if you do, please let me know. I think it's very fascinating to discuss. With that, if you guys have any more questions, I know we're almost out of time, but I want to make sure I'm here to support you guys.
Yeah, definitely. That was fascinating. I'm sitting here with a guy I was sharing a room with, and we were watching and saying, "That is so cool!" How
in a scary way, but cool, yeah.
And it's just getting started, and that's the problem. And give this another year or two, a couple years, yeah, it's going to be amazing what it's going to do.
All this has happened since December. This paper was published in December. Like, it's 3 months. Yeah. Yeah.
All right, folks. Well, I'll give everyone a minute. We have a hard hour today, so I'll have to cut the feed here in a second. But the chat will stay open. So if people want to stay and ask questions, that should be perfectly fine. If not, this will go live on YouTube next week, and you can always ask your questions there in the comments. And as I see them come through, I'll ask Ankur to come answer them.
Sure. And as a quick side, I think my email address is in the presentation. We'll send the slides. Feel free to email me if you have any questions or want more references to anything deeper here. I'm happy to talk about them. I'm doing a more technical version of this paper next week. So if you guys are interested in that, let me know, and I'll send you a link to that as well.
Fantastic. And we'll also have notes out for everyone next week. So if you're here, you're probably on the email list, so you'll get all that information. But with that, again, thank you, Ankur, for hanging out with us.
Yeah,
this was really informative, and I hope folks got a lot out of it. And everyone out there on the live stream, we'll see you back here in a couple weeks. Thanks so much.
Great. Thanks, guys.